Hello, hello, hello. How you doing? It is Thursday, the 13th of November. I'm on a little bit earlier than the promised 9:30. I had some cancellations and I decided that 9 p.m. would be a far preferable end time to my day than 10:30 would be. I see we already have someone in the chat, so I apologize for being 3 minutes late. Um, I've got some questions I want to go through when we're doing sort of our interview prep. And this is specifically what I call these developed questions. So in the interview, I've been through how my interview went. I've been through the graph sketching skills. I've been through some derivation skills, but there's some questions you get when you've never seen it before. Because as I always say, it's a lesson, not a test. And so sometimes they want to test your ability to learn as if it was a lesson. Different people from different courses and different backgrounds will have different training in different parts of the syllabus. And so what they sometimes want to do is to give everyone something that's completely brand new, just to get everyone on the level playing field. So everyone will look at these questions and go, oh God, I've never seen anything like that before. And kind of think, oh, what do I do about that? So I want to give you some skills for how to handle those situations, how to keep calm and still show your best work. So I have 3 case studies I want to go through, plus I had a specific recommendation for a topic, which was permutations and combinations. So my first case study is going to deal with that. So I'm just going to lay out a few problems and talk about how you might handle them. And as always, I see we have 2 people. If you have questions in the chat, feel free to drop them in. As opposed to my live solves, I'll be much more attentive on the chat. So hopefully I'll be able to get to those as soon as possible. I think, actually, no, I'll do a little bit of prep work on this. So I'll say there's 2 types of problems I'm going to go through today. The first is what I call a developed problem. This is one where it starts off easy and I push it a little bit further and a little bit further and a little bit further until you get a sense of a bigger idea that links it all and you come away having learned something. I kind of introduced this when I talked about my interview. That was drawing sine x and then drawing sine squared x. Starting off easy, developing it a little bit further. Another type of problem is the looking at a brand new equation you've never seen before and doing something with it. So that would be kind of like the Arrhenius equation that I got in my interview. So I'm going to handle a little bit of both. And I'm going to start, I think, with the developed idea. So we're going to start off easy and build up so you get some bigger understanding. And I'm going to use permutations and combinations as a case study. Bad preparation on my part. Apologize. I'm just going to get the Miro whiteboard up so I have something to actually write on. How's your day going? I am so tired, but it is fine because I could still do this. My brain is still functioning just enough. So, all right, let me share screen. We just need the whiteboard today. How's yours? My day's going good. That's the good thing. Now that half term's over, everyone's back to school. It means I actually have my days back again. So when it was half term, it's just like going and going from 9 a.m. till like, can you imagine working a 9 till 5? Oh, terrible. So yeah, now it's a bit more, calm. You get your days, chill. My day sort of starts at like 2 p.m. All good. So, right. Let's get into this. So we're going to start with permutations and combinations as per request. So I'm going to start with this question. Let's say we have a postman who has to deliver packages to 4 houses. What is the probability? And something has gone wrong, so all the labels have been removed from the packages. So what he does is he assigns the packages randomly to the 4 houses. 4 packages, each going to a house at random. What is the probability that none of the packages end up at the correct house? So this is where a developed question is likely to start. Small, in hand, where you can kind of brute force it, use a bit of sort of common sense and a bit of process to work your way through. Maybe you don't know how to do that systematically. That's fine. So you just brute force it. The first thing you might think is, how many possibilities are there? Well, if there's 4 houses, there are 4 possible packages I could deliver at the first house. Once I've done that, there are 3 packages I can deliver at the second house. Then there are 2 packages I could deliver at the third house. And there's 1 remaining package to deliver at the last house. So multiplying all those together, I get 24 possibilities. 24 is in hand enough. I'm just going to list them out. And what I'm going to do, because this is an interview situation, you don't want to bore them. Realistically, they wouldn't ask something like this. That would require so much brute force, but I'm still going to commentate about the fact that I'm doing this in a nice, systematic, ordered way so that I can make absolutely certain I'm not missing anything. So I'm only permuting sort of one thing at a time, doing them in roughly sized order, and then just swapping the 2 at the end to make sure I cover everything. And because I've already done that work beforehand, I know exactly how many to expect. And if worse comes to worse in an interview situation, you don't have to worry about wasting their time. You do whatever it takes for you to demonstrate what you know, even if it means listing out all the possibilities. So lastly, 4, 1, 2, 3, 4, 1, 3, 2. Oh, and by the way, while we're here talking about this, if they do decide they don't like a method, they'll just intervene and give you the skill on the spot. And if they want the lesson to go a specific way, they'll have to let you know. So don't feel bad about that. Right, so we've got our possible combinations. And again, we're going to go through in a nice systematic way. So we can cross off any possibilities where 1 has arrived at the first house. We can cross out any possibilities where 2 has arrived at the second house. We can cross out any possibilities where 3 has arrived at the third house. And we can cross out any possibilities where 4 has arrived at the fourth house. So that leaves us with 1, 2, 3, 4, 5, 6, 7, 8, 9 possibilities out of 24 for all the packages arriving at the wrong house, and then simplify that to 3/8. So that's a kind of brute force way of doing permutations. If anyone's done IB, then you can think of this in a slightly different way. So you could think of this as being, there are 4 places. I have 4 packages to place in 4 spots. And that is 4 factorial all over 1 factorial. If you know sort of permutations, if you don't, that's fine. That's something they can kind of teach you. So this, great. We've grounded ourselves. We know how this starts. Now let's build it up a bit. So not so much for this, because obviously if this scales, we're not going to be able to write out every single combination precisely. But now let's consider, in fact, we can kind of still use this to demonstrate the idea I want to do next. So instead, we could consider, all right, we've got 4 things. How many ways do we have of arranging them all? And we've just established the answer to that is 24. So then they might ask you this. In how many of those does the 1 come before the 2? Starting off, you can brute force this again and say, okay, the 1 comes before the 2, certainly in all 6 of these. None of those. That one, that one, that one, that one, that one. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and I'm missing one. 12. So 12 out of 24, which is a half. And then they might say to you, does that make sense? And you can go, why should that make sense? Because the 1 and the 2 are definitely involved in every single one of these permutations. So there's only 2 options. Either the 1 is before the 2 or the 1 is after the 2. So clearly in half the cases, the 1 is going to be before the 2, and in half the cases, the 1 is going to be after 2. So that makes sense why that would be a half. And they say, good. And then they might develop that idea a little bit further. What about this? What about how many combinations are there? How many permutations such that 1 is before 2 and 2 is before 3? Gets a little bit harder. Okay. So that might be, well, that has 1, 2, 3. That has 1, 2, 3. These do not have 1, 2, 3. Nope, the 2 is in the wrong spot here. The 3 is in the wrong spot here. We have 1, 2, 3, and that's it. So that's only 3 out of 24, which is an eighth. I think there should be 4. I think I'm missing one. This one. Apologies, I did miss one. And that's the danger of doing a sort of systematic approach here. So that one there, 1, 2, 3, 4. So it was actually 4. And in the real thing, they could have just pointed that out. They could have said, oop, just have a closer look. Small execution error. They're not going to hold that against you. But what they're going to do now at this point is say, teach you the new skill. Okay, so as we restrict it more and more, generally there's 24. If the 1 has to come before the 2, it's 24 possibilities. If the 1 has to come before the 2 has to come before the 3, you're down to just 4 possibilities. Is there a way we can scale up that understanding? And the way they're going to teach you the new skill. And here's how it works. If the 1 comes before the 2, which comes before the 3, you can just consider those 3 numbers and the different ways that those can be arranged in amongst everything else. So regardless of what else is happening, if we have a 1, 2, 3, you can think about those combinations. And there's going to be 6 ways of arranging those. 1, 2, 3, 1, 3, 2, 2, 1, 3, 2, 3, 1, 3, 1, 2, 3, 2, 1. There's 6 ways of arranging these numbers. And in only one of those rearrangements are they in the correct order of 1, 2, 3. So therefore, regardless of what's happening around it, only in 1/6 of the possibilities will the 1, 2, and 3 be in the correct order. There were 24 possibilities, 1/6 of that is 4. And the same thing worked when we needed the 1 to be before the 2. 2 possibilities, they can be arranged in one of 2 ways. And in a half of those cases, therefore, is the 1 and the 2 going to be in the correct order. Great. Lesson learned. Let's apply that. Let's develop that idea. Now this time, we are going to take the letters of the word Cambridge. And we are going to rearrange them randomly. Question 1. How many possible permutations are there? And the answer is, there will be 9 possibilities for the first letter, 8 for the second, 7 for the third, so on. So therefore, there's 9 factorial possibilities for permuting there. And then they might say, in how many of those permutations do you get the C followed by the A followed by the M? And this is where the most important thing happens. So whatever you thought you knew coming in, if they've taught you something in the moment, seize onto that as if the meaning of life is in it. And think about doing nothing else but using that skill. So you're going to think back and you think, all right, how did we do it with the 1, 2, 3? Well, what they did was they ordered them and then considered how many, or rather what fraction of those were the correct ordering. So if I consider the CAM, there's going to be 6 possibilities. CAM, CMA, AMC, ACM, MCA, MAC. So there's 6 possibilities, and only in one of those are they ordered correctly, regardless of what's happening around them. So what I know is, regardless of how I permute all of these, 1/6 of those cases will have the C followed by the A followed by the M. So 9 factorial over 6 will be the correct answer. You obviously can't do that. You don't have a calculator, but that would suffice. And then they might say, all right, let's do a different style of question. How many permutations would have the A before the B, before the C, before the D, before the E? Because we have A, B, C, D, E in it. They don't have to be right next to each other. So it doesn't have to be precisely, why is it 9 factorial and not 8 factorial? Because I can't count to 8, that's why. Oh, glorious. Thank you for that. Because I can't count to 8. Oh. Oh, no, because Sorry. No, it's even better. It was 9 factorial. It's because I can't spell Cambridge. Oh, God. Don't you love it live? All right. So it was 9 factorial. That's because I can't spell Cambridge. Oh, God. Thank you for that. Always pick me up if I'm making a mistake. Oh, we're calm, we're collected. It's fine. And also, if you make a silly mistake like that, it's perfectly okay to laugh in the room to break the tension. Just so because if you make a mistake like that and you think, oh God, then it might like give a sense of insecurity, like you think that what you did was bad and reveals what you're actually like. Whereas, look how I reacted. I laughed because I knew that was nothing like what I actually am. Like I'm like, I can count to 9. I can spell Cambridge. These mistakes don't mean anything about me. You can kind of play that off in the room, and they'll actually quite like the dynamic. Obviously, sets it out. Maybe if you get like a sort of really grizzled sort of interviewer, maybe you won't want to play that trick. But yeah, you're fine. Anyway, so having correctly spelled Cambridge and having correctly counted to 9, let me calm it down. Let me slow it down. Let me get back into the train of thought. So the problem was, in how many of these permutations does the A come before this B, come before the C, come before the D, come before the E, where they don't have to be right next to each other? We can stick the M in between, the G in between, blah, blah, blah. There's stuff happening around. Let me try and generalize what we did before. So before, we considered all the way, we isolated just the C, A, and M, and we permuted all of them, and there were 3 factorial ways of arranging those. So I'm going to apply the same thing here. Well, how many ways are there of arranging these? 5 factorial. And only in one of those arrangements are they in the correct order. So this fraction of the total number of permutations will have those in the correct order. So the answer would be 9 factorial over 5 factorial. Which, while we're here, actually does simplify. Because that would be 9 times 8 times 7 times 6 times 5 factorial, all over 5 factorial. So that actually would cancel. And you could conceive of a situation where they give you something that would be reasonable to calculate. So I think that's a good way of sort of, A, introducing P's and C's. And 2, thinking about this sense of a developed question. Starting off small, something that's very in hand, and building and building, having to learn lessons on the way to handle the biggest problem at the end. I'll give, while I'm here, I'm close enough. I'll give one last one that I think this one I've given is less what I would expect to come up in an interview. A version that could come up in an interview, though, is about handshakes. So number of people in the room and how many handshakes are possible. So let's say there are 3 people in the room. One shakes 2 hands, one shakes 3's hand, and 2 shakes 3's hand. So that's 3 handshakes that happen. If there are 4 people in the room, You get these shaking their hands, and those handshakes as well. And so you can think about a way of scaling this up. Let's say instead there were 10 people in a room. How would you work out how many handshakes there were? And you could start by saying, all right, how many? So 1 shakes the hand of everyone from 2 till 10. So 1 shakes 9 hands. 2 has already shaken 1's hand. So 2 has 3 to 10 to still shake the hands of. So that's 8 people left. Possibly, or there's handshaking them up. I'm going to be honest, don't know it. And because this is in the developed problem, total valence equals 2 times the number of nodes. Yes, and we're going to talk about why. So it's good that you know that. If you have that knowledge, absolutely feel free to bring it into the room, because if anything, that's quite impressive, and they like the fact that you've read up around the topic. And it gives you an opportunity to demonstrate it. You solve the problem quickly, and then you can get to more questions in your allotted time, and it's just good all around. So yeah, if you've got that prior knowledge, bring it to the room. If you don't have that prior knowledge, don't worry. It's a developed question. They can teach you, because it's a lesson, not a test. So the point is, you can add up all of the numbers. Sorry, that's a plus 3 plus 2 plus 1. Anyone who does any killer Sudokus will know that sums to 45. But there's actually another way of proving this, which is thinking about combinations. So from the 10 people, in order for a handshake to happen, you have to choose 2 of those 10 to shake hands. So actually, the answer is the same as 10 choose 2. Out of 10 people, choose 2. How many different ways are there of picking 2 people to shake hands? And from your binomial, you know that's 10 factorial over 8 factorial 2 factorial, which you can simplify down. So 10 times 9 times 8 factorial all over 8 factorial 2 factorial. Those cancel. And that's 90 over 2, which is 45. Or, as Michael said, total valency would be 10 times 9, because person 1 sees 9 other people, and each one of those 10 people see 9 other people. So 10 times 9 is 90, and then you divide that by 2. I think that's roughly what you were saying. Right. So having addressed that, let's go on to topics I think lend themselves a little bit better to these developed questions. So I'm going to pivot now from the math into physics. I'm going to start with a simple resistor array. All of these resistors are going to be identical, just resistance R. Ooh, that's good. I'm not even sure. So we've got a question about whether someone has the interview. I don't think the interview offers have come out yet. Yeah, I think it's too early for that. So I think, in fact, the ESAT results only come out this week. Am I right? They come out on like Thursday or Friday. Yeah. But still, a lot of people are prepping ahead of time because they only let you know about interview offers like so late in the game. I'll let you chat this out. Wait, some already have interview offers. Ooh, that's early. Oh, I didn't know that. I don't expect interview offers to come through until like late November, with only like 2 weeks notice maximum, which is why you often have to prep ahead of time just to like be ready to pounce. But right, okay, let's get into this. So let's consider the resistance between points A and B. So with this simple array, it's in hand. You get to start where you're comfortable. This is, thank you, dude. So this is sort of a parallel paths, right? We have 3R, we can simplify this. We have 3R up here. We have R down here. Oh, tomorrow. Okay, good to know. I'll check up on my students. Is it tomorrow? Yeah, it is tomorrow, isn't it? All right, thanks for that. So we have R down here. We know how to handle resistances in parallel. So we know that 1 over R total is going to be 1 over R. And even if you find this easy, I think it's good just to sort of show that you can go through the motions. Because if you skip steps, they just want to see it at least once just to verify, right? So I'm just gonna, even though I know I can do this, I'm just, it's gonna be 3 and 3. It's gonna be 4 over 3r. And then our total, we're gonna flip it around and we get 3/4 r. Engineering, I'm gonna get to an engineering problem. That's the next one. So that's our first case. And then they might say, okay, great. What about now? Ooh, no, oh man, I was gonna have a moment. It was gonna be a whole thing. All right, nope, you go back. Let me actually get the pen back out. What about now? You might say, so oftentimes when people see this problem, they kind of want to, like we did the first time, they want to draw it out. So I'm going to leave that first. So the first case was 3/4 r. And then a lot of times people want to draw this out. So we see this. We know there's a branch on the top with 2 resistors on it. And we know that then goes through a resistor to B. And there's also a path which just goes through a resistor to that point. So the question is, what's happening here? Well, I'm going to apply what I know. I know there's no resistance on that path. And I know that therefore there can be no voltage drop. There's no potential difference on that path. And because that path is in parallel with this path, there can also be no voltage drop across those 2 resistors. But because V equals IR, the only way that's possible is if there's no current in that path. So that gets short-circuited, no current flows through there, it all goes through the 0 resistance path. And then it actually just simplifies to 2 resistors in parallel. You can follow through the physics on that, but that will give you a half R. Cool, we solved that. Now, this is the part where it becomes a developed problem. In any sort of situation, they might teach you a new skill to apply to even more complex challenges, which is the whole point of today. So here's your lesson. In a circuit, if you have 2 points with no potential difference between them, they are functionally the exact same point. So I can rename that. That is also A. No current is going to flow from A to A, but I now have 2 parallel paths that go from A to B. And this technique can help you simplify complex circuit diagrams, especially when there's like crisscrossing and all sorts of, whatever happening. So that's the skill. Hold on to that, because that is the one thing you should use moving forward. They make it more challenging still. Let's add another crosswire. Okay, well, using the skill the interviewer just gave you, if these 2 points, and these don't intersect, so these 2 points are connected by a wire, there's no potential difference between them, these also become the same point. So now how do I get from A to B? Well, there's that way, there's that way, there's that way, and there's that way. And that's exactly the path that the current would take. So it would go up here, left through here, and down through here to get to B. Or up there, down there, straight there, up there, and sorry, to get from A to B, I drew that one wrong. That should have gone down. So there are 4 parallel paths going from A to B, and I'll let you do the math on that. That would be 1/4 R. We're not done yet. Let's make it a little more complicated still. Let's extend this resistor array. Let's get rid of everything. All my little arrows. No, actually, I did want to keep those. Whatever, I'll redraw it. It's fine. Okay. Okay, what about now between the A and B? Let's take it let's build it up. Let's apply it. These 2 points, same. These 2 points, same. These 2 points, same. These 2 points, same. How do I get from A to B? 1 path, 2 path, 3 path, 4 path, 5 path, 6 path, 7 paths. And so by applying the same logic, it would simply become R over 7. And so they teach you that new skill on easy problems and build it up and build it up and build it up so you can handle problems. If I started off on this circuit diagram and asked you to find the resistance, no shot, unless you've seen this before. And so that's what they're doing. Giving you a new skill to solve problems. Can you apply it? And that's the aim of a develop question. What was the other one? Okay. So the other style I said I was going to go over is when they present you with brand new equations you've never seen before. And Michael, if you are still here, I really do hope you have never seen these before, or else this is going to all be for waste. But I'll show you how you would handle it if it is an equation you've not seen before. So we're going to consider beam deflection, which is an important idea in engineering especially. This is going to be important for for instance, building bridges, where you don't want it to buckle and bend. You're considering what materials to make things out of. So let's lay out the situation. Still here. Well, let's see if you've seen this already. So let's say we've got a beam between 2 pivot points. Typically, you will have seen a setup like this in moments, in mechanics or in physics. And typically, you're making an assumption that that is a rigid rod, which cannot bend. We're about to break that assumption. So what we can do is we can apply a force, and instead it will bend. So you can imagine a situation where applying that force makes it deflect downwards, and it sort of gently bends under its own weight. And that deflection, we call delta, has known equations. In fact, I've got them written down, but I just realized I forgot to take down one of those parameters. So I'm going to look it up very quickly. Just to make sure I know exactly what this parameter refers to. In that case, if I can't find it quickly, I'll give up. I think that's it. Where was that defined? No, not for L over 2. Give it one more shot. Nope, not that. Oh, I can't see that. All right, I'm gonna leave it. Okay, I'm just gonna define it a certain way. If it's not the right definition, but again, it almost doesn't matter because they have to give you this equation for it to work. So let's say that this force is being applied at distance b from this pivot. And let's say that L is the distance between the pivots. I think that's how it's defined. Apologies if it's not. This equation definitely works. So let's look at this equation and see what we think. So the formula for the deflection is the force you apply over the Young's modulus of the material. Sorry, 48. The Young's modulus of the material times the second moment of inertia, which is a quantity you've either seen before or you don't have to care about for the purposes of this problem. This. So you've never seen this before, but you can still be expected to use this. So we're going to use this to work out where to apply my force to get maximum downward deflection. That is clearly an optimization problem. So apply the skills you do know how to use to handle this unknown situation and get information about this brand new equation. So I know if I differentiate and set to 0, I will find with respect to B, because that's how I'm varying where the force is applied, I'm going to find the position where applying the force gets me my maximum deflection. So let's differentiate with respect to B. That would be 3L squared minus 12B squared. And I know that will equal 0 at the point of maximum deflection. This will not equal 0, so I know that 3L squared equals 12B squared. Apologies, let me flip that around. So 12B squared equals 3L squared. So B squared is equal to L squared over 4. So B equals L over 2, which feels intuitive. If you really want to bend that thing, you're going to apply the force halfway through. And another thing we can do with this is to plug that back in and work out what that maximum deflection will be. So the deflection would be F over 48 EI into 3L cubed over 2 minus L cubed over 2. Now, okay, let me not do this too much in my head. Let me do it the way you would do it in the real thing. I am technologically competent and know how to erase things. Right. 3L squared L over 2 minus 4 into L cubed over 8. So simplifying that, this becomes F over 48 EI. This is not going to challenge you too much, but you do it, you get, so you get your 3 over 2 L cubed minus your half L cubed, which is obviously just L cubed. So FL cubed over 48 EI. Done. And what they can also do, by the way, is get you to interpret the equation. So we did this in the derivations where you derived equations and then made predictions based on those equations. They could also present you an unseen equation and get you to make predictions on the spot. So for instance, does this make sense? How would I maximize the deflection I get? Well, applying more force clearly is going to maximize the deflection. And Young's modulus. If I use a material with a smaller Young's modulus, so that's bendier, that's less stiff, I'm clearly going to get a larger deflection. That makes sense. And if you were handling this too well, they might even delve into like what I is. It's even something you might have done or might end up doing if you do AQA physics. One of the options I know is engineering. And the textbooks are available online if you want to learn more. I'm going to do a similar problem now for more of a diving board situation. So instead of having 2 pivots, let's just have the 1 pivot anchored at the wall. And let's apply the force some way along that. So let's say the thing is of length L. I apply force downwards at A, say, where A is over here. The length is L. This is definitely defined correctly, by the way. The deflection in this case would be given by F over 6 EI 3LA squared minus A cubed. Cool. In theory, if you're doing engineering, you will eventually get to the point where you can derive this. But for now, for an interview situation, they would just present it to you as given. Let's do the same thing. Let's find out. Well, in fact, you can make a prediction. Just based on common sense, you know where to apply the force to get the maximum deflection. It's going to be at the end. But let's see if we can prove that. So you think, okay, I know what I'm going to get. Right. Okay, let's differentiate this. So let's differentiate with respect to A. So we're going to get F over 6EI into 6LA minus 3A squared, which equals 0. So 3A, well, in fact, so let's do this rigorously, which might impress the interviewer. So we would say 6LA minus 3A squared equals 0. Let's take a 3A out, and you get 2L minus A equals 0, which means that A equals 0 or A equals 2L. And at that point, you stop and you interpret that result you just got, and you go, wait, what? Because A can't be 2L because the thing's only L long, and it can't be 0 because if you apply it there, it's just not going to deflect. There would be no moment, like it wouldn't do anything. So then you think, hang on, what's just happened? Why is my math failing me? And that's when you kind of keep your cool and go, okay, this just might be a different situation. Maybe if I graph this sketch, it will reveal something. So if I think about that deflection, that's F over 6EI. I can take an A squared out, and I'm left with 3L minus A. So that means I know I'm going to have roots, not just roots. I know I'm going to have a root when A equals 0. So if that equals 0 when A equals 0 or A equals 3L, but I know a bit more because that's A squared. I know this will be a turning point. So I know there'll be a turning point at A equals 0, and I know it will go through 3L. And this is A minus A cubed. So based on the shape, I know it should come from here, go down, come up, go down again. And I know this turning point should be at 2L. But I know practically, based on the engineering constraints of the problem, A versus delta, well, delta versus A on this graph, but A only exists between 0 and L. So it is still the case that the maximum deflection occurs when A is equal to L. It's just that's not a turning point of the delta expression, which I think is an interesting result. And they could possibly use that to trap you out, thinking always about the interpretations of your results and whether they make physical sense. So in this case, we can plug that in and think about what the maximum deflection would be. The maximum deflection is actually when A equals L. And so you get 6EI, 3L cubed minus L cubed, which is obviously just 2L cubed, which then turns it into FL cubed over 3EI. And where this could go in an interview situation is maybe they want to use this idea and talk about exactly what you would use to build a diving board, for instance. So maybe you understand something about I. So maybe you understand that if I make the board a bit thicker, it's going to be harder to bend because that increases I. So to make a nice springy board, I might want to use a very thin piece of wood, but not so thin that it like snaps at the point that somewhere along the diving board. And you might have then a more open-ended conversation about what materials to use, something like that. But hopefully this sort of shows what to do if they hand you a brand new equation, just sort of bolt from the blue and expect you to use it. Are there any equations? That's a good equation to use. Trying to think. Yes, there's another one I like to give. And again, I'll tailor this for engineering because I know we've got engineers in the house. So let's say they give you this equation, which actually, strictly speaking, is kind of on the ESAT syllabus, and yet no one ever knows it. So I'm just going to give it anyway. Which is, if we're considering thermal conduction from hot to cold, that's governed by this equation, where the rate of thermal energy transfer through the well, it doesn't even have to be a conductor, but through the solid, where this is the thermal conductivity, this is the cross-sectional area, and this is the temperature gradient. And we're going to use this to solve what actually is a problem that came up on an ESAT style paper in the past. I can't remember if it was NSAA or ENGA. But we're going to consider a situation where we have something hot on this side, something cold on this side. And we're going to consider what happens when we have a thin insulator and a thin conductor in some order. So in the first case, we're going to consider the conductor on this side and the insulator on this side. And in the second case, I just want to make sure I don't cover you with my face. So in the second case, we're going to swap them around. And we're going to think about what the temperature profile might look like through these materials. So if that's the hot side, that's the cold side. So swapping them around, that's the insulator, that's the conductor. So the question then becomes, how does this equation give us information that we can apply to these graphs? Well, what do I know? I know that energy flows from hot to cold. So energy is going to flow from the hot side to the cold side. I also know at this boundary, energy cannot be created or destroyed, which means that the energy into that boundary has to equal the energy out of that boundary. And what that means is dq dt has to be the same on both sides of the boundary. What else do we know? We know that conductors, thermal conductors, have larger thermal conductivities than insulators do. We know they have the same cross-sectional area, and that will inform us about what the temperature gradient must look like through the material. And again, we're going to assume that they have the same thickness. So for the conductor, it has a higher thermal conductivity, same area, and the same dq dt. So therefore, the temperature gradient must be a lot smaller. And for the insulator, the temperature gradient must be a lot bigger to compensate for the smaller thermal conductivity. So in this case, it will look like this, and then this. And as always, you might think about whether this result makes sense physically. Because it might be intuitive to think, hang on a minute, a conductor is really good at conducting thermal energy. So surely it would be able to, have a huge temperature gradient through that, sort of transferring the heat through it. Not so, because if you think about the real world, if we have, for instance, a cup of coffee in a styrofoam cup, the whole point of wrapping it in an insulator is that it can maintain that temperature gradient between the hot liquid on the inside and the cold air on the outside without having that energy transferring through it. So insulators are able to maintain temperature gradients like this. It's literally their whole point. And the whole point of conductors is to conduct through it so the temperature is the same on both sides. That's how saucepans work. You want the hot flame on the underside of it to be the same, you want the water to become the same temperature as the flame. So it should be constant temperature throughout. That's the whole point of a conductor. So these make sense based on physical understanding of conductors and insulators in the real world. So that's how the equation applied to the graphs. And now I think I'm going to apply this to what I think is one of the coolest things in all of engineering. And I think I'm still right about this. It's been a while, so don't quote me on it. But I remember this moment of learning this and thinking, what the hell? This is the coolest thing ever, right? So I'm going to give it to you guys as well. And in fact, this really serves our purposes because I can give you what for you might be a new equation. Let's consider engines. Jet engines for planes flying in the sky. We clearly want them to be as efficient as possible to minimize fuel waste. I can give you an equation for the efficiency of an engine, which you may or may not have seen before. The efficiency, eta, is 1 minus T cold over T hot, where it's not a one-to-one here, but if you think about how engines work, they take cold air from the outside, they heat it up by burning fuel, that heating up of the air causes it to expand, creates pressure, it goes flying out, and you get some momentum change, so therefore you get propelled forward. So it's this ratio of the cold air on the outside and the temperature you heat it to. So they could ask you, okay, what would you need to do to maximize the efficiency of an engine? So you would say, okay, well, I would clearly need to minimize TC or maximize TH. And then you go, hang on a minute. What can I do about TC? That's the air outside. I can't control that. So the only thing you can control is TH by making it as hot as possible. The hotter you run an engine, the more efficient it is. So then the question becomes, in engineering constraints, what is the limitation for how hot you can run the engine? So it takes the cold air in, heats it up in the hottest part of the engine to this hot part. You've got the turbine blades going around. Those turbine blades are made of metal. So clearly, the limiting factor here is the melting point of the metal. If I run the temperature too hot, the turbine blades melt. Bye-bye plane. And so the question then becomes, all right, what can I do to try and protect my metal blades in the heat of the engine to try and push the temperature up as high as possible? And the answer is this. What you can do to keep this temperature of the metal still below the melting temperature, but coating it in an insulating ceramic with a high melting point, you can actually get this massive temperature gradient, which means you're running it, the actual hot air that the turbine blade operates in, can be hotter than the melting point of the metal. And when I learned that, it blew my mind. And I think the exact figure was it's about 200 Kelvin above the melting point of the metal. And that's what keeps planes in the air, is effectively learning how to engineer it to keep an ice cube solid in an oven in terms of temperature difference there. Absolutely wild engineering. And in case you're curious, by the way, what they also do, they got these little turbine blades, so they coat them in the high temperature, the high melting point insulating ceramic. They also have air channels running through it, constantly blasting cold air through, and so that any heat that does make it through to the metal gets quickly pulled away through a massive flow rate of cold things, sort of cooling it from the inside. Wild piece of engineering, that. Okay, so hopefully that makes a bit of sense about how to both develop questions, because I think, do I have enough time? I might have a bit of time to go through one more. I'll take recommendations if you've got a particular topic you want to go over. I'll also take recommendations if you have a preference for which of the two to go through. Would you prefer to see unseen equation and just deal with it? Or would you prefer to have that developed so it starts easy and builds up harder and harder and harder? Because I think I have something that can work for both. Also happy if nothing comes through. Actually, I think I know what to do. I think I'll go through amplitude envelopes, because I think I can do that fairly quickly. Both. I can't do both. I've got a session at 8. I'd rather do one slowly and develop it right. But I will say, Michael, that's the attitude. If you present that attitude, they'll be like, oh, yep, one of us. Let him in. What I'll do is I'll teach you about amplitude envelopes when it comes to graphing sinusoidal curves. So let's plot sine x between minus 2 pi and 2 pi. So it does something like that. As you know, the amplitude goes between 1 and minus 1. I trust that you would be able to fill out the rest of the position, the other things. But let's consider what happens, for instance, y equals 3x. Well, we know what that does, right? It makes it get taller, so the amplitude now goes between 3 and -3. So here's your skill. This is y equals 3 sine x. What we're going to do is consider this to be a function of x times sine x. In this case, the function of x is just y equals 3, just a constant 3. So what you can do is plot. We're obviously going to assume I drew that accurately. We're going to plot the lines y equals 3 and y equals -3. The reason why is because sine x varies between 1 and -1. And you will spot that wherever sine x is equal to 1, it touches this y equals 3 line. And wherever sine x equals -1, it touches this y equals -3 line. So, by considering what goes before my sine x, if I plot y equals that and y equals minus that, wherever sine x equals 1, it will touch y equals the function. And wherever it was sine x is -1, it touches that. So for instance, let's consider the case where y equals e to the minus t times sine of t. And again, if they teach you something, you drop everything and you use it. And ideally in the exact language they gave it to you. So mimicking that exact language back, we consider this thing, we draw y equals that thing, exponential to k, and y equals minus that thing. And wherever sine was equal to 1, it will touch the y equals e to the minus t curve. And wherever sine was equal to -1, it will touch the y equals minus e to the minus t curve. So we'll do something like this, where the period will stay the same and the amplitude will get smaller over time. So in fact, this might make even more sense if I call it cos t. Because we can see it will start up here at 1. And then, by the way, you might think in this specific case, well, okay, well, what happens? This looks like a special point because I would have expected it to be flat, but I'm wondering if this does other nonsense because it can't be above this curve anymore. It has to sort of stay below the curve because the whole point is these functions, amplitude envelope, these functions determine the maximum that the amplitude can ever be. So it can never be above this line. So what's happening here? Okay, let's differentiate and find out. Equals e to the minus t times minus sine t. So this is product rule, first d second, plus second d first. So that's a minus e to the minus t into sine t plus cos t. Let's find out what's happening at t equals 0. That would be minus 1, 0, plus 1. So the gradient would be -1 there, which is why it's not 0. It goes sort of straight down. And you will, of course, recognize this as being lightly damped oscillations. So what did you do? You took this function, you drew y equals that function, y equals minus that function. Wherever the sinusoidal equaled 1, it touched y equals the function. Wherever the sinusoidal equals -1, it touched the y equals minus the function. Let's make that a little bit harder still. Let's see how that applies to y equals x sine x. Okay. So I'm just going to apply the same logic. I trust it will serve me well. Y equals x. Y equals minus x. Sin x is initially equal to 0. And again, it's a special point, so let's find out what's happening there. Because initially I would expect sin x to do something like that, but there seems to be some nonsense happening. Let's find out what's happening. To get its behavior, as always, differentiate. So differentiate x cos x plus sin x at x equals 0. That would be 0 plus 0, so it's 0. So I know it's going to be flat through the origin. And wherever it was 1, it's going to do this sort of thing. So it was 1 at pi over 2. Yep. And every 2 pi after that. And it was minus 1 at 3 pi over 2. But now, let's think about this. Where was, at minus pi over 2, the sin x graph, which I can draw for reference as an important component graph. So at minus pi over 2, it was equal to minus 1. So it should be on the y equals minus x line. And so it kind of flips around and it starts doing all of this. And you see it's becomes symmetrical, where all of these points that were equal to minus 1 now get flipped into the positive because they're being multiplied by an x, which is negative. And so it just gets now this nice symmetry to it. And if it's something you're into, you can then describe it in terms of even and odd functions. You can go into a bit more detail about what the coordinates of these points actually are. It gets a bit interesting. But in terms of applying this idea of an amplitude envelope, that's how it's done. So you can see they can develop the skill with like a simple graph, teach you a new technique, and get you to apply it to situations and interpret those physically. So right, I'm going to have to stop there because I'm trying to be good and keep these to an hour where I can. So it's not overwhelmed. And I also got, oh, wait, sorry, yes. Happy to wait for this question. I've got the session in 10 minutes, so I've got time to answer it, but I just wanted to make sure I had good wind down time. For the previous example, yep, all right, I'll get it back up. Tree prep. Just wait for that to come through. And I'll monologue in the meantime for anyone watching this after the fact. So yeah, I think that applies. Are you sure you use the product rule correctly? Let's find out. The one before this. No, I'm not. First d second, so that cos differentiates to minus sine, plus second d first. If you differentiate, I think I am right. Because if you differentiate, I could do it a bit more slowly if you want, but so this one, I know that cos t will differentiate to minus sine t. And I know that if I differentiate e to the minus t by the chain rule, that becomes minus e to the minus t. Yeah. And so that gives you that. That's where this minus came from. So it was plus minus e to the minus t times cos t. Not an idiot. You made an execution error. Not the same thing. Okay. So hopefully that all makes sense. But I think to summarize, I think that's a really important skill, which is why I wanted to spend. We were working with. Right. Okay. Sin t instead of cos t makes sense. So, but hopefully that core idea that I've been really trying to go into today makes sense of what to do when they throw you something you've never seen before. Don't get overwhelmed. They are giving you the instruction. So just take whatever they give you and use it to the best of your ability. Combine that with the skills you already have from the syllabus. Keep your senses about you to interpret your results and think, does this make sense or do I need to do something else? But that idea that ability to play with new ideas is one that they're really looking for. You can never guarantee what you're going to get in an interview, but something like that could happen. You could find a moment like that. And rather than panic, if you think, it's a test and I don't already know how to do this, you can take your breath and think, no, this is a lesson, not a test. I'm about to have the best lesson of my life. Because that's what an interview is. It is your first ever supervision or your first ever tutorial. And so hopefully that's the exact one where you kind of rub your hands together and go, oh, I'm going to walk out of this interview better than I walked in, and this is going to be great. Both when it comes to slowly developing an idea or just being thrown into the middle of an equation you've never seen before. So hopefully that gives you some good stuff to think about. I am still working on the schedule, so I should be able to go live sometime around this time next week. Hopefully, I'll put a community post out when I know exactly what my Thursday schedule is, because my people earlier in the day are all kind of starting to move around. But I'll always make sure to populate the stream well in advance so that you know when it's going to go live, and I'll try and post something if the timing is going to change. So with that, carry on what you're doing. Keep practicing, work hard, have fun, and I'll see you guys next time. All right, take care.